Okay. Then I'll share the screen. Okay. Thank you. Now, initially we said, okay, we have a rigid body, this five-sided figure, at position 1 at t is equal to 0. And then we have moved this rigid body to position 2 at time t is equal to 1. We have frozen the time. We are looking at the two positions at the same instant, okay? Whereas they do not occur at the same time. Now, this is the original motion. Right now, I have a fixed frame, this square that I have drawn. This is the frame that I am looking at the motion. If I'm sitting on the moving frame, on this five-sided figure, and looking at the motion of the fixed frame, in that case, looking at the moving fixed frame, then instead of this, for the same relative positions, the second position of the fixed frame will be like this. What will happen is, you see the distances, A1, A2, is equal to A2 prime A1. That vector, A1, A2 vector, will be equal to A1 prime, A2 prime A1. And B2 prime B1 will be equal to B1 B2. Because it is the same motion. Is that right? Now, in this case, you see, what I have done is, I have determined P12 for the original motion by drawing the perpendicular bisectors to A1, A2, B1, B2. Here's the P12. If I draw the perpendicular bisectors to B2 prime, B1, to A2 prime, A1, they intersect at the same point, P12. The difference is, in the first case, if the moving body, I'll hide these lines because I don't want it to make it complicated. In the original motion, if the rigid body has rotated about P12 by an angle phi12, in the inverse motion, this rigid body will be rotated from the first position to the second position for this inverse motion by the same angle, but in opposite direction. This angle will be equal to this angle. I don't know how it was. Yes, the two angles are exactly the same. So if I invert the motion, look at the fixed frame from the moving frame, the pole, the rotation pole is the same, but the angular rotation of the fixed frame relative to the moving frame is the inverse, is the negative of the original motion, is minus phi12. Now, it's very simple. If you are going to determine the inverse motion, it is, the pole is the same, but it is the angle that is minus phi12. Now, where can I use this? You see, when we were designing a 4-bar or slider crank mechanism, etc., we first selected A1, A2, our moving pivots. We had two parameters for the moving pivots. We could select A1, A2, B1, anywhere on the moving frame. And then we were able to determine the corresponding center point, fixed pivot, on the perpendicular bisector. In that case, selection of a point A1, the moving pivot, required two parameters. The selection of the center point required one parameter, correct? In some cases, in most cases, this is possible because you are free to select A anywhere you like, B anywhere you like. But in certain problems, you want to select A0 first, center point first, and determine the circle point next. The thing is, once you invert the motion, in the case of a 4-bar, if, in the original 4-bar, these moving pivots, these are the moving pivots, they are on a circle. These are the fixed pivots for the original motion. If I invert the motion for a 4-bar, this coupler link is fixed now. What happens is the circle point and center point change their role. Is that right? If you fix the coupler link, you release the fixed link. Now, what was the center point is now the circle point. What was the circle point is the center point. Okay? So, in this case, what I can do is, I can select at any point A0, anywhere you like on the moving frame. And then determine A02 because I can determine it very easily because it's going to be a rotation about the probe P12 by an angle minus phi12. Draw the perpendicular bisector. Now I can determine A1 anywhere on the perpendicular bisector. I can determine A0 anywhere I like and A1 on the perpendicular bisector. Any questions? Now, in certain problems, this was an exam problem that I did several years ago. In spaceships, you are going to carry solar panels. The solar panels, when you are orbiting the spaceship, has to lie tangent to the surface of the spaceship so that it doesn't occupy too big a space. It doesn't you have any resistance. When you move up, when you are in the orbit, you want to turn the space panels 90 degrees so that it gets the sunshine. Now, in this case, the fixed pivots cannot be placed anywhere you like. The pivots, fixed pivots, must be on the ship's surface, on the surface of the ship. It has to be, let us say, a 2-meter diameter. It has to be on this circular arc. Is that right? You cannot place a fixed pivot over here or over here, because it's going to, when you are going to the orbit, you have to confine it. You have to reduce the resistance, right? Everything must be in a confined space. Can everybody see that? You cannot place A0, B0 anywhere you like. So it has to be on the surface. So you select A0, B0. Now you have to determine A1, B1 on this solar panel. So in certain cases, this is usually true in most machinery. If you have a structure, let us say the machine structure, body, fixed body, you have to place your joints at or near that rigid body. So you first select A0, B0, and then determine A1, B1 on the moving body. Okay? Because of this, this gives us an ease to determine A0 arbitrarily anywhere we like, and then determine A1. Let me go back to GeoGebra. Now, you see, originally, let me move this back like this. Originally, I was able to select any point CD on this moving body, determine F4 bar. Now I can select a point, any point I like, as C0. Let me call this point C0. C-0. This is the center point, correct? Now I can determine the location of C0 in the second position. All I have to do is, I don't have to do this, but to show you that what I'm doing, I'll do it like this. That angle is alpha. I will rotate C0 P12 by an angle alpha, but the original angular rotation phi 12, which is alpha, is in counterclockwise direction. Now I'm going to make it clockwise direction. Can everybody see why? Oh, no. No, it shouldn't be there. I think 312 degrees is the problem. Okay. 1 second, I have to change it. It has to rotate in clockwise direction. So I'm sorry, I'll delete this and measure this angle in a different way. A2, P12, A1, P12, A1. Okay, yes, that's correct. That angle is alpha now, 48 degrees counterclockwise. Now, rotate C0 P12 by an angle alpha in clockwise direction. Yes, here it is. This point is the location of C0 in the second inverse position, renamed as C-02. This is the second position. Now I can draw the perpendicular bisector to C0 to C1. I can select C1 anywhere on this moving body, five-sided figure, anywhere on this perpendicular bisector. Let me select exactly what we have done previously. This will be, rename it as C-1. I can select another point, C2, okay? D0, and determine D2. And that will be a 4-bar mechanism that will move your moving body from the first position to the second. So using this inversion, I can select C0 and then determine C1. I can select the center point or fixed pivot, determine the circle point using this inversion. Any questions on this? All you have to do is, you are going to use the same pole, but the angular rotation for the inverse motion will be opposite to that of the original motion. Okay. Any questions? Okay. I will say this if you want to look at it later, you can do so. Besides the inverse motion, now we have another problem. In the previous case, we have two planes, one fixed, the reference frame, the other moving frame. What if I have three planes? I have a fixed frame and I have two moving frames. I have two moving frames. One I call E, the other I call E prime. These two moving frames have two positions, E1, E1 prime at time t is equal to 0. At time t is equal to t1, E2, E2 prime. So we have the poles, rotation poles. If you are sitting, observing the motion from the fixed frame, you have, according to Schall theorem, these two planes most simply move from the first position to the second by a pole P12 located at the perpendicular bisectors of two pairs of homologous points. The same thing for two planes. Now, this is the case. I have two moving frames. This is the motion, correct? The new question that we are going to ask is phi12 is 64 degrees, psi12 is equal to 35 degrees, okay? The question we have is, what if I am sitting on plane E and looking at the motion of the plane E prime? What if I'm sitting over here and looking at this plane? What will I say? What kind of a motion will that be? Is that agreed? Now, in order to do that, what we do is we fix the plane E that I show in blue in one of its positions. The relative positions must be the same, by the way. The relative positions for these two positions, it's fixed. So what I do is like this. I will fix the two planes in the second position. Let me do it like this. I will make these two lines color red, just for the hell of it. Hide the labels. Usually I don't like the labels. Unnecessary, of course. I fix the two planes at this position, at the second position. Now I subtract the motion of the plane E from these two planes. What I mean by subtraction is bring A2B2 to A1B1 and C2D2, move it such that it is a rigid body with A2B2, okay? So that these distances are the same, meaning rotate E and E prime both about P12 by an angle minus phi12 prime. Why the hell did I put let me change this. That shouldn't be prime. Okay. I don't know why I have it. Okay. By an angle minus phi 1, 2, so that A2, B2 goes back to the first position, A1, B1. Now I have fixed all these, and I will rotate all these back to the first position. In effect, I'm subtracting the motion of the plane E from that of E prime. This is how I will do it. Rotate this point, or no, absolutely not that. Rotate around the point, this rigid body, about P12, by an angle alt phi dash 1 dash 2 in clockwise direction, because phi 1, 2 is clockwise. Now I'm moving it back to the original position. Yes, here. Move, rotate this line about P12 by an angle alt phi dash 1 dash 2. Oh, sorry. Can anybody tell me what mistake I made? It should be clockwise. Because it is minus phi 1, 2 that I want to rotate. Okay? And rotate this line. What happened? Alt dash 1 dash 2. Oh, again, I made the same mistake. Now, please note, the motion A2, B2, C2, D2, this is a rigid body motion of a simple rotation about P12. Now, what I will do is I will change the names. This point will be C prime dash 2. And this point, it says, okay, rename as D prime dash 2. Okay. Now, the motion that I will see if I were sitting on the on frame E would be the motion of C1 D1 to C2 prime D2 prime. It will be again two positions of a moving frame. I will be seeing CD at two locations, correct? The motion from that I will see will be C1 D1 would not be moving in clockwise, counterclockwise direction if I were sitting on the fixed frame. I would be seeing the motion of E prime as a rotation of 35 degrees counterclockwise about P12 prime. If I were sitting on plane E, I would be seeing the motion of the plane E prime, it will not be a rotation about P12 prime. It will be a rotation, according to Schall's theorem, a rotation about some other point, which we shall determine. And the angular rotation would be, you see, originally C1 D1 has rotated by an angle 35 degrees, psi1 2, to second position. But in this inverting, when we are subtracting the motion of E, bringing E2 to E1, what we have done is we have rotated both bodies, both rigid bodies, by an angle minus phi1 2. So that means the angular rotation from C1 D1 to C2 prime D2 prime will be equal to, can somebody tell me what that angle will be? Yes, you can turn on your, let me read. Originally, if I were sitting on the fixed train, the motion that I will see would be the motion for E prime, a rotation about P12 prime by an angle psi1 2. What I have done is for E prime, I have rotated to C2 D2 by an angle psi1 2. And then I have subtracted, I have rotated it back by an angle phi1 2 about P12. Yes, can somebody tell me what that angle will be?
Phi plus psi.
Psi1 2 minus phi1 2, because I have subtracted phi1 2. Correct? Both being counterclockwise. This is psi1 2. First, I have rotated. You see, this is an important thing. In plane motion, angular rotations are additive. In spatial motion, it is not additive, but in plane motion, they are additive. First, I have rotated this plane by an angle psi1 2, and then I have rotated this plane by an angle minus phi1 2. Can everybody see that? They are additive. So the angular rotation from the first position to the second position relative to E is a rotation about the pole, which we shall find, by an angle psi1 2 minus phi1 2. Okay? Now what I do is, as I have done before, to determine the pole for this relative motion of the plane E prime relative to E, to determine the relative motion of this plane, plane, what I do is, since I have two homologous points, D1, D2 prime, C1, C2 prime now, this is the relative motion of the plane E prime with respect to E. I draw the perpendicular bisectors to D1, D2. Draw the perpendicular bisectors to C1, C2. These two perpendicular bisectors intersect at one point, according to Schall's theorem. This is the rotation of the moving frame E prime with respect to the moving frame E. This I will call relative pole by R dash 1, 2, 1 dash 2, and I will name give a name 1. R121. That is the relative pole. Remember we said, let us show what we have said is true. The angular rotation of C1, R12, C2 R1, C2 prime R121. This angle should be equal to 35 degrees minus 64 degrees, which is, yes, 19 degrees, right? Am I correct? 19 degrees. Let us check that. But sorry. It will be 331 degrees. Yes, 331 degrees because it's taking it counterclockwise. As I said, 35 degrees counterclockwise minus 64 degrees clockwise. Because not minus 64 degrees clockwise is 19 degrees or 331 degrees counterclockwise. Is that agreed? This angle is psi 12 minus, sorry, psi 12 minus phi 12. Any questions? This is the relative motion. Now, if you have two bodies moving, now you have a relative motion and relative pole. But unlike you see, P12 or P12 prime, we said is the only point that is fixed, that has the same location for the first and second positions on the moving frame. R121 is the only point common for these two planes at that first position. Okay? The reason I called it 1 is it is in the first position. Since the two planes are moving, R121, when the plane E moves to E2, R121 is not going to be at the same location this time. It is a common point between the two planes, E and E prime, but since the two planes are moving, R121 will also move. Okay? Now, you see, I have P12, P12 prime. Those are the rotation poles for the plane E and E prime relative to the fixed frame. Now I have R121 in the first position. That is the relative pole of the plane E prime with respect to plane E. Any questions, please? Let me take another. I will open another. I will save this and then open this one.
Hocam, before closing this window, can I ask my question?
Of course, I'll stop.
So I understood what we obtained from these operations, but I couldn't get what the figure is representing. The figure below.
This C2, D2 prime, you mean?
Yes.
If you are sitting on the plane E, okay? Would you be seeing the motion of the plane E?
No.
No. Exactly, this is what I have done. I have subtracted. I said, okay, This is the second position. These two positions are the second positions of E and E prime. Let me fix these two to each other, okay? And move them back to the first position of E. The first position of E is A1, B1. So what I have done is I have subtracted the motion of the plane E from that of E prime. This is the motion that you're not going to see. Motion of E from first position to the second. But since both of them have moved, what you will be seeing is, if you were sitting on this plane, you would be seeing C1, D1, and then this moving plane has moved to C2, D2 prime, relative to this moving frame E. You see, the distance B2, D2 and A2, C2 is exactly equal to B1, D2 prime, A1, C2 prime. This is a rigid body. These two are the rigid bodies. Let me show it like this as well. What I have done is I have fixed those two planes and subtracted the motion of E. I have moved it back. Okay? So E prime, E double prime is the motion from E1 prime to E2 double prime is what I will be seeing if I were sitting on E in the first position. Is that agreed?
Okay,
that is what I will be seeing. That is the relative motion of the plane E prime with respect to E. That is the relative motion. Okay?
Okay, John. Thank you.
Now, I have determined, you see, R121 is this point. It has rotated by an angle gamma 1, 2, this relative motion. And gamma 1, 2 is psi 1, 2 minus phi 1, 2, because I have subtracted the motion of phi 1, of E from E prime. This is the relative motion, let me repeat. Okay, let me go back. I will open another file. This is the same thing, but I have the two positions. This is the relative pole. I have this P12, P12 prime. Now, that's the relative pole. I can move, this is important, C1, D1 to the second position as follows. First, I can, you see, this is the relative pole. These are the P12, P12 prime. I can move E prime from C1 to D1 to C2, D2 by rotating it about P12 prime by an angle psi 1, 2. I don't know why the hell I have this. Okay, I hate it. I can move C1, D1 to C2, D2 by a rotation about P12 by an angle P12 prime by an angle psi 1. Or else, what I can do is, I can first rotate C1, D1 relative to A1, B1 by an angle psi 1, 2 minus phi 1, 2 about R1, 2, 1 by an angle yes, by an angle psi 1, 2 minus phi 1, 2 about R1, 2, 1. Let me do that. You see, let me repeat. I can move C1, D1 to C2, D2 by a rotation about P1, 2 prime by an angle psi 1, 2. Or else, what I can do is, first I can rotate C1, D1 about R1, 2, 1 by an angle psi 1, 2 minus phi 1, 2. And then I can rotate that position about P1, 2 by an angle phi 1, 2. Let me do that. Let me take this line as well. One line I'll take to show you. First thing I will do is rotate about this point. This time I'll do it like this. Phi dash 1 dash 2, sorry, psi dash 1 dash 2. But I don't know what psi was. Yes, no. No. Okay. I forgot how to type psi. So I will turn on the keyboard. I haven't used keyboard till now. Here's psi. What happened? Dash 1 dash 2 minus alt phi dash 1 dash 2. Okay? This is very clear. This is rename D dash 2, sorry, D prime dash 2 C prime dash 2. This is a rotation of C1 about R1, 2, but 1 by an angle psi 1, 2 minus phi 1, 2. Let me also rotate this. Oh. Okay, that's exactly where it is. Now, once I'm over here, now what I can do is I'm going to rotate A1, B1, C2 prime, D2 prime, and R1, 2, 1, R1, 2, 1, all these, I'll fix these, all these objects, fix them to each other, and rotate everything about P1, 2 by an angle phi 1, 2. This will bring C2, D2 prime to C2, D2. Is that okay? This will bring A1, B1 to A2, B2. This is what I have done before, so I can tell you. Okay, I'll show you that it's true. And then R121 will move somewhere else. Let me first, I think this is obvious. A1, B1 will go to A2, B2. I'm not going to do this. But I'm going to rotate C2 prime, D2 prime about P12 by an angle phi 12 to show you that it moves to C2, D2. Rotate this C2, D2 prime, C2 prime, D2 prime about P12 by an angle alt F dash 1 dash 2 in counterclockwise direction. Can you see that? It has become M and N. It is at the same location. Okay? I will rotate this line, since I have fixed all those. Think of, okay, let me say this. Think of A1, B1, this plane E and E prime, extending everywhere, and there is a point R121 common for E and E prime. Okay, two planes. Now, if I rotate this line about P12 by an angle phi 12 in counterclockwise direction, here is R121. But now it is the second position of the plane 1-2, 2. Now this is the second position of the moving frame E, because the moving frame E has rotated to the second position by when we have rotated everything about P12 by an angle phi 12. This is the second position of the relative pole R12. This is the first position of R12. This is the second position of R12. Now, let me hide a few lines, a few things to I'll hide all these. Okay, well, okay. I think I can do that. It will take some time, but oh. I will hide these. I'll keep the poles because you see, the motion is not defined. I could have picked up any other point A, B, C, D. So it is not important. What is important for when two positions are specified, it is the angle phi 12 and P12 that is important. Okay, those are the invariants. Those are what does not change. Whereas all other things do change. Now I have P12 prime. Let me move it like this so that you can see that. Here is R12. If I need, whenever I need, I can turn on those lines. Let me draw these lines. And this is P12, P12 prime. Here's the line. Let me make that line like this, P12, P12 prime line. Extend it like this. You do it like that, okay. Now I'm representing the motion of plane E by the pole P12 and an angular rotation phi12. I'm representing the plane E prime by a rotation psi12 about P12 prime. R121 is the location of the relative pole between these two planes in position 1. Okay? Now, please, what can you say about the angle R121, P12, R122? What can you say about that angle? That angle I have obtained by rotating R121 about P12 by an angle psi12, phi12, sorry. I have rotated this R121, P12 by an angle phi12, correct? This, the second position, in the first, you see P12 relative to the fixed frame, P12, P12 prime does not change. When I move to the second position, R121 goes to R122. It is a common point between the planes E and E prime, both planes. It is a common point between the two planes. If it is a common point between the two planes, it has to remain common for the first position and for the second position, so that the distance R121, P12 prime must be equal to the distance R122, P12 prime, and the distance R121, P12 must be equal to the distance R122, P12, because it's a rotation of the two planes. Both planes have rotated to the second position, and this is a common point for both plane E and E prime. That distance has to be kept the same. When I move R121 from the first position to the second, I have rotated it about P12 by an angle phi12. This angle is phi12. But notice, when I can obtain the same thing by rotating R121 about P12 prime by an angle psi12. And these are the same. So that means, number one, P12, R121, P12 prime is equal to P12, R122, P12 prime. These two triangles are mirror images about P12, P12 prime. Okay? I can obtain R122 in three different ways. I can rotate R121, P12 by an angle phi12 about P12. I can rotate R121, P12 prime by an angle psi12 about P12 prime. Okay? Or else, what I can do is draw a perpendicular line to P1 to P12 prime. Take the image of R121, the distance, let me show this point. The distance, I'm not going to call it P, call it Q, or any other name. Q R121 is equal to Q R122. It is the image of R121 with respect to the line P12, P12 prime. Now, another thing. In that case, these are similar triangles. So the angle R121, P12, R122 is bisected by the line P12, P12 prime. So this angle is phi12 over 2. The angle R121, P12, R122 is phi12. This angle R121, P12Q is phi12 over 2. Similarly, this R121, P12 prime, R122 is psi12. So R121, P12Q is psi12 over 2. These angles, psi12 over 2, phi12 over 2. Psi12 over 2 and phi12 over 2. So that means I can obtain, rather than going all that drudgery, I can obtain the relative pole R121 as follows. Locate P12, P12 prime. Those are the poles relative to the fixed frame. Measure minus phi12, minus psi12 with respect to the x P12, P12 prime line. Draw lines making an angle phi12 and psi12 from P12 and P12 prime. Those two lines are going to intersect at R121. You can determine R122 by simply taking the image of R121 with respect to P12, P12 prime. Okay? Any questions? Where the hell am I going to use this? Okay, let me have a break first, 10-minute break, and then I'll start. Where can I use this? Where can I make use of it? I'm giving 10-minute break. If you have any questions, I will be glad to answer. I'm here. But if you want to go somewhere, etc., you can do so. I'll start at 10. Oh, I stopped the. Where the hell is the cliche? Recording. share screen. Okay. Now, the question is, how am I going to make use of this relative pole? As you will see later, we can make lots of use of it. Number one, correlation of crank angles. You see, if I have two cranks, links 2 and 4, I want, when one of the cranks rotates by a certain angle, phi 1, 2, I want the other crank to rotate by another angle, psi 1, 2. I want to determine a 4-bar mechanism that will realize this motion. Given the correlated two crank angles, as one crank rotates by an angle phi 1, 2, the other crank has to rotate by an angle psi 1, 2. I want to design a 4-bar mechanism. Very simply, I have two methods. I will tell you two methods, and then I will solve both of the cases. What I can do is, I can determine relative pole R1 to 1 by an angle, by drawing a line that makes an angle minus phi 1, 2 from A0, because in this case, A0 is P1, 2 for this moving body. This is a crank, and it is moving. I'm sorry, there's some noise coming, so I have to close my window. Okay. P12 is one pole, P12 prime is the other pole, because it's permanently a rotation. So those are my two rotating bodies. So I draw lines making an angle psi 1, 2 over 2, phi 1, 2 over 2. The point of intersection is going to give me relative pole R1 to 1. Now, I draw any line L1 passing through R1 to 1. This line can be anywhere. And then draw another line L2 that makes an angle alpha, which is equal to A0 R1 to 1 B0, is equal to L1 R1 to 1 L2. Now I can select any point A1 on L1, any point L2, A2 on, any point B1 on L2. That 4-bar mechanism, the mechanism that I will obtain, will satisfy the given crank angles. The reason is, if you remember in the first lecture, I said, when drawing the pole, we said the cranks subtend the same angle at the pole. The coupler link and the fixed link subtend the same angle at the pole. It is true for this case as well. Now, when you have R1 to 1 is a relative pole, if A0A is fixed, B0B is your coupler. So A and B are circle points and center points. They have that relation. So you can select A1, you can select B1 on L2, A1 and L1. You have the 4-bar. But the thing is, in all these cases, the theory tells you that the mechanism will exist at two positions. It says nothing about the motion in between the two positions. Because of that, you have to check. You have to check your result. Okay, that's very important. Another method is, this is one method, using of R12, determining R1 to 1, and then drawing these two lines, selecting, or in another way, what you can do is you can select A1, determine B1 on L2. Okay? Now, another method is, okay, let me select B0, B1. If I select B0, B1, if psi12 is given, I can determine B0, B2. These are the cases. Now, what I can do is invert the motion, meaning keep A0, I don't know where A1 is, but keep A0, A1 fixed, keep that link crank fixed, release A0, B0. If A0, B0, A0, A is going to rotate by an angle phi 1, 2 in between the two positions, and if I invert the motion, keep A0, A1 fixed, then A0, B0 and B0, B1, B0, B2 has to rotate by an angle minus phi 1, 2 about A0. Let me repeat. If I invert the motion, B0, B1 is rotated to B0, B2. I have assumed B1, location of B1, somewhere over here, and then determined B2. If I keep A0, A fixed in the first position, then, and look at the motion of the other links, A0, B0 has to rotate by an angle minus phi 1, 2 to keep the same relative positions. And B0, B2 must be rotated by an angle minus phi 1, 2 about A0. So rotate everything about A0. This is the position of B1, B2 relative to A0, A, the other crank. Okay? Now, if you draw the perpendicular bisector to B1, B2 prime, A has to be on that line. A1 has to be on that line. Okay? This is what we do, kinematic inversion. This time, we keep A0, A fixed. These two are circle points. We determine A. Okay? That's the idea. Any questions? Okay, let me do one example. First, I will do it in one case, in both cases. Again, I will turn on file new. This time, I have saved that, if I'm not mistaken. Okay. I have a new file. Let me close it. As 160-degree counterclockwise rotation for phi 1, 2. I'll take 60 degrees counterclockwise rotation for psi 1, 2. Okay. What I will do is, I can arbitrarily select A0 over here, B0 over here. I will rename this point as A-0, and I will rename this point. I have taken you can take this 1 unit, 10 units, whatever you like, B-0. When you are correlating crank angles, the fixed link length can be increased or decreased. It doesn't matter. Font size, let me make it large. Okay. Now, let me draw the slide like this. I'm going to 160 degrees counterclockwise angle for phi 1, 2, and 60 degrees counterclockwise angle psi 1, 2. I first determine R1, 2, 1. I'm going to draw a line that makes an angle minus, okay, let me do this like this, input, phi dash 1 dash 2. Sorry, I have made two mistakes. Alt phi dash 1 dash 2 is equal to 160 degrees. Honestly, I don't know how to type psi. Psi dash 1 dash 2 is equal to 60 degrees. Correct? Those are the two angles. Now what I do is, I can do both ways, but I'll take angle with a given size. Alt phi dash 1 dash 2 divided by 2. Since phi 1, 2 is counterclockwise angle, I have to take it, it is minus, I have to take it clockwise angle. 80 degrees, I think it's over here, right. So I draw a line. That's the line. And then I draw another line. Okay, I think I can do that as well. Psi dash 1 dash 2 divided by 2. Again, clockwise. Draw that line. I can hide this line point. The point of intersection is going to be R1 to 1. Okay? Now, what I'm going to do is, I will do it like this to show you something. Yeah, I think I can do that. This is the first time I'm doing this, so please bear with me. An angle, okay, it's comma, comma. Okay? Rotate this angle. By gamma. Counterclockwise, okay, fine. Over here. If I bring it over here like this, then I will call L-1, draw this line, and then I will measure this angle A0, R121, B0. That is epsilon. Okay. Now, rotate this line. By epsilon. Oh, no. Okay. I have to use this. Where is epsilon? Yeah, here. That is counterclockwise. This is counterclockwise. Now I can draw this line. Oh, no. This line I will call L2. I can pick up any point on this line L1, call it A1. Pick up any point on this line, call it B1. The 4-bar mechanism that I have A0, A1, A1, B1, B1, B0 is going to satisfy when A0, A1 rotates by an angle 160 degrees, B0, B1 will rotate by 60 degrees counterclockwise both. Now, I have how many parameters? Number one, I can change this gamma. Can you see that? Two, I can change A1, B1. I can change A1, I can change B1. I have plenty of solutions, very many solutions. Let me hide these lines now. I'm not erasing them, I am hiding them so that so I have infinitely many solutions. I can change this. I can change this. And I can change this. Now, this is the mechanism in the first position. Let me also erase the labels. I'm not erasing them, sorry. I'm simply hiding them. Now, I have to check. I have no guarantee that this mechanism is movable in between the two positions. I know that the mechanism is going to exist at these two positions. I can prove that. I can show that. But I don't know whether it is going to be movable in between the two positions. So, very simply, This gamma is design parameter. You have you're able to select A1, B1 on those lines. You could have attached slides for that, but I didn't attach slides for A1, B1. You can also attach slides because these are one parameter. It has to be on that line L1. This has to be on that line L2, as you can see. You cannot move anywhere. So 1, 2, 3 parameters. You have 3 design parameters. Correct? Now, if you want to analyze this mechanism, select another angle variable. This is not a design variable, it is a position variable, right? Theta. I'll do it very simply. Angle with a given size. Theta, counterclockwise. Oh, by the way, I will select that. I didn't. This has to be from 0 to 160 degrees. So, oh, no, sorry, 160 degrees. Okay. Like this. I'll call this point, rename it as A. And then I have to show the label. No, I don't need that. I mean, that is enough. B0, B1, B will be on a circular arc, circle. Oh, sorry. I will draw a circle, another circle, with center A, radius L, correct? Now notice, let me move it like this. This is the intersection, correct? This is going to be B, agreed? Hide these circles. My 4-bar mechanism, A0, A, B, B, B0 at position theta. And the crank angle is theta. It doesn't satisfy 60 degrees, as you can see, because it's, let me show you what happens. If you take B or make it cross, okay, let me show the 2 circles and show why that is so. If I had this intersection point, if I dismantle the mechanism and join it like this, okay, and measure this angle, it is 60 degrees. Can you see that? So this solution that I have right now with me is not a valid solution. As I said, not all the mechanisms, or there are 3 parameters, is a possible solution, is a candidate for a solution, but you have to check. In this case, let me repeat, you have to, the second position does exist. but it does not exist at the place where you want it, because you have to dismantle the joint. Is that okay? Only in that case you can assemble it in the second position. So you cannot move. I think in this case I will. Okay. Let us search for some other solution. Let me hide this. No, I don't want to move that. What happened? Oh, I made a mistake, I think. In this case, yes. Oh. Okay. Oh. No, I have moved to the other way. I think this will work. Yes. For example, this is a solution. This is a possible solution. I don't like it, but it's a possible solution. In this case, I have the mechanism assembled in a different form. Okay. As you can see, I have to switch it back. Okay, I think I'll do that. You see, I have the other solution, so I have to, okay, let me do it like this. Delete this point. Call that point B. Show. Now I have this 4-bar. Correct? In the general position. As you can see, for when I move to 160 degrees, B1, B0, B is 60 degrees. When one crank rotates by 160 degrees, the other crank rotates by 60 degrees this time. Any questions on this? This is the possible solutions. It's quite good. Next, I'm going to save this.
Hocam, can I ask something?
Of course.
Before you made the last changes, the mechanism was moving such that the B link was moving 60 degrees at the end position, but it was not increasing always. It was like first increasing and decreasing to 60 at the last position. Was it a valid
It is
solution
possible
still?
because you see, you have to search for a correct and a feasible solution. That's what's important, okay? You have to see whether the mechanism is assembled in one way or the other. You see, a four-bar mechanism, when you have a certain crank angle, has two positions, two solutions, okay? Open or closed form, we call it. And it is possible that the two positions you have is in the two different branches of the four-bar, what we call it. So you have to check all these things. You cannot possibly, although you have so many parameters, although you have so many solutions, some of the solutions will not be feasible. You cannot use it. It is not a possible solution. You have to check it. For every problem you have in mechanism synthesis, you must check your result. You see, the theory tells you that the two positions will exist. But it does not tell you anything about the motion in between the two positions. This is going to be true for 3, 4, 5 positions as well. You have to check. You have to check your result. Okay?
Okay, hocam. Like, I was curious about, like, if our goal was to obtain angles that will be as desired at the final position, or should they be like
increasing or decreasing, you say?
Yes.
Depending on the problem, that may be a very important thing that you have to think about. Okay? Depending on the problem, let me repeat. I mean, in certain cases, you may want the mechanism move continuously in an increasing or decreasing manner. But in certain other problems, that small change in the direction of motion may be beneficial in certain problems.
Okay, hocam. Okay? I get it.
But let me repeat, usually what you say is true. You would like to have, when given two angles, phi12 and psi12, you would like to have both of them increasing, monotonically increasing functions. But it depends on the problem. This correlation of crank angles, which we'll be discussing later, analytically much more in detail. But right now, let me say this. It depends on the problem. Okay? You can do lots of things with it. Right now, it is the simplest way of doing things. It's two positions. It's the simplest. You have to understand the concepts that we are going to, the methods and the concepts in this case, because we shall be using the same construction ideas for 3, 4, 5 positions, etc. But the problem is going to get more and more complicated, or the problem is going to get more, two positions. Let me say this, two-position problem is the most simple, but the most useful problem, solution in most cases. It occurs, in lots of cases, you see this problem. But later on, we shall add more positions, okay? Now, let me solve the same problem. I save this file, 4bar1, file new. I will solve the same problem like this. I will again select A0 and B0. Okay. And then I will select a point B1. Okay. I want B1 to be over here. And I will rotate B1, B0. Oh, sorry, I will type phi dash. What happened? Oh, this. Alt phi dash 1 dash 2 is equal to 160 degrees again. Degrees. Psi dash 1 dash 2 is equal to 60 degrees. I'm solving the same problem right now. I will rotate B1, B0 by an angle psi dash 1 dash 2 in counterclockwise direction. Oh, did I do it wrong? Oh, cancel, 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 cancel. I think I have used by mistake the other phi, not this one, but that one, okay? Okay, this point is going to be B2. I have rotated, I have determined the two positions of this crank, B1, B0, B1, B0, B2, B0. Okay, now what I'm going to do is, let me draw this A0, B0 line. I'm going to rotate A0, B0, B2 about A0 by an angle minus phi 1, 2. Rotate about around the point. Sorry, sorry, minus, or I'm not going to write minus, I'll say alt phi dash 1 dash 2. Since phi 1, 2 is counterclockwise positive, I'll take clockwise. Rotate clockwise. Okay? Oh, I have rotated, I'm sorry, I have rotated about B0. I'm sorry. Rotate. Oh, I rotated it wrongly. Alt phi dash 1 dash 2 clockwise, like this. B1 to B0 has rotated to this location. I will call it B prime 2 dash 2. Rename it as A prime dash 0. This is the position of B0B, so not A0. Is that correct? Maybe I have done something wrong. I'm not sure. let me check. Oh, yes. This is B0, this is B2 prime. I have labeled them wrong. Okay. Let me show that the distance A0, B0 prime is 10 units. Yes, it is 10 units. As you can see, it has rotated. I have rotated B2, B0, A0, about A0 by an angle minus 512. Now, if I draw perpendicular bisector to B2, B2 prime, it has to pass through A0. I can select A1 anywhere on this line. The 4-bar mechanism that I thus obtain let me hide this. A0, A1, B1, B0. When I rotate A1, A0 by 160 degrees by an angle 512, B1 will move to B2. Let us check that. Again, I'm not sure whether I can have it or not. Okay. Counterclockwise. Oh. That's a circular arc. It's of length K, as you can see over here. The point of intersection is over here. Show object. This is my 4-bar mechanism in any general position theta. As you can see, it moves back and forth. Let me change B. And let's see whether this, again, as you said, as your friends they mentioned, it moves back and forth. But it doesn't move to the second position. I have to dismantle it to move to the second position. Let me do it like this. No. It's funny. I think I will have it like this. No, I have to. Sometimes it becomes very distressing. I have to disassemble and assemble in this case. I cannot reach to the second position, as you can see. Let me do it like this. Unfortunately, I will try to find it later, okay? Right now, I am not able to find a good solution for this case. No, this won't work. Oh, yes.
Hocam, can it be about the intersection of the circle A?
Right now I have to change the intersection. I have to take the second branch. Yeah, that's why. But I will do this later, okay? I mean, I don't want to spend too much time on this. But of course, I will save this file. I will correct it, 4x1, 4x2. You have to spend some time, okay, to find a good solution. And you have to check which branch it is and so on. Okay. Okay. Usually you have a good result. You have to check. Another thing is, if you have to correlate crank angles, there's what I will call linearization or Archimedes principle. Yeah, I'm sure you have learned this in high school, maybe even in primary school. Archimedes lever is something which we all know. If I have a lever with a hinge over here, SA, the displacement of 2 points A and B, is proportional to the distance A0B and A0A. Correct? These displacements. And in that case, using the same principle, what we can do is consider two cranks parallel to each other, okay? A0, B0, and select a B0B, A0A. The angular rotation, this displacement S, if you consider both of them parallel, will be almost the same. You know, it will be a vertical line S, the vertical distance S for both of those cranks, correct? That those joints will be displaced by an amount S in both cases. That length S, that arc length S for both cases will correspond to an angular rotation psi12. B0, B psi12 will be equal to S. A0, A phi12 will be equal to S. That arc length. It is approximate, it is not exact. Because those two arc lengths are not the same. Those are that's the chord, in fact. Can everybody see that? If you want to have the angular rotations different, B0 will be on the other side. A0 or B0 will be in opposite sides of that displacement. Correct? So what you can say is psi12 is equal to A0A over B0B phi12. Okay? So if you want to, the given phi12, psi12, for small angles, for angles up to 50 degrees, 60 degrees, for phi12 and psi12 up to 60 degrees, you take the midpoint, make phi12, psi12, select A0A and B0B, according to, if you are given phi12 and psi12, you take the ratio of A0A and B0B, do it like that. This works quite well for small angles. No, it is a very simple and very easy way of solving. The thing is, especially in machines that were designed much before than the Industrial Revolution, like textile machines, like some other machines. This, I believe, is the basic idea that people have used. Because this is linearization. It is simple, as you can see. But this will not work for large angles. The error will increase as you increase the angle. For instantaneously, this will be correct. This will be exact. For a very small differential rotations. For larger rotations, this approach will not work too well. Okay? This is an easy thing to solve. Can I correlate slider displacement with crank angle? The answer is yes, of course. In this case, P12 is over here. Where is P12 prime? The pole for the slide, for this case. It will be at infinity, correct? So what you do is, you can determine the same relative pole. P12 is over here. P12 is at infinity in vertical, perpendicular to the slider axis that you have defined. It is perpendicular to the slider axis. What you can do is, you can again determine the relative pole, R121, by measuring an angle minus phi12 over 2 from P1 to P12 prime, Notice P1 to prime line will be a line perpendicular to the slider axis passing through A0. And then if S12 is given from 1 to 2, measure, instead of measuring an angle psi12, this time you have to measure minus S12. Because S12, in that case, if P12 is at infinity, S12 is the chord length. It refers to the angle. So you measure a distance S12 over 2 to determine R121. Once you determine R121, well, this is exactly what we have done in case of 4-bar. You know the R121, you select L9, L1, passing through R1, L1 and L2, and you determine A1, B1. L1 here, yes, here is A1. L2 is the slide. The angle L1, R121, L2 must be equal to A0, R121, P12 at infinity. Okay, that's it. Or if you use method 2, you invert the motion. You can invert the motion and determine the motion of the slide with respect to the A0 and perform it like that. Or you can fix B1 the slide. You can determine A1, A2, and displace A0, A2 by a distance A0, A1 by a distance A0, A2 by a distance minus S12 to determine A2 prime, and select B1 on the perpendicular bisector to A1, A2 prime. Your direct inversion. Let me repeat, you must check your result. Your result, you must always check your result. Any questions? Let me read. In this case, what I did is I selected A0, A1, determined A2 by the given phi12, and then I displaced A0, A2 prime, A2 by a distance minus S12. Here's A0 prime, A2 prime. Now, this is the position of A2 of the crank relative to B1. I have subtracted the motion of the slide from that of the crank. Subtract the motion. Draw the perpendicular bisector. Select B1 anywhere on the slide. Okay? That will move your 4-bar from the first position to the second. Now, I can use this relative motion concept in lots of places. Let me give you an example. This is design of 6-link mechanisms. Here I have a lamp, I have a table. I want to have a lamp that I can move from one place to another on the table, 1.5 meters in fact. But the problem is, of course you can design a 4-bar. However, I don't want to have fixed pivots anywhere. You know, I want to have a post for the lamp that I can place on the table on one side. So I can only place my fixed pivots in one region, in this region. I cannot place it anywhere else. if I'm going to have a post. This is the fixed pivot. And I want to have my moving pivot on the lamp to be within this trapezoidal region. I don't want it to be anywhere else, right? In this case, if I tell you these two constraints, you will not be able to find a 4-bar mechanism solution for this problem. Is that agreed? The pole is at infinity, P12 is at infinity. Select any point A1, determine A2, draw the perpendicular bisector to determine A0. It will not be passing through this rectangular area. If I select A1 over here, A2 over here, A12 will be a line like this. I can select A0 anywhere on that line, but that's no good. I want my moving pivots, fixed pivots over here in that region. Can everyone see that? So in such a problem, you see, we do not complicate mechanisms for mechanism's sake. We do not use a 4-bar if we can solve something using a rotary motion or sliding motion. We do not use it. We always try to design something simple. If you cannot satisfy your requirements by a 4-bar, then you have to search for another mechanism of 1 degree of freedom that has more joints, that has more links, that is more expensive to manufacture, that's more complex. So if you cannot solve your problem with a 4-bar or a slider crank, now you search for another solution, 6-link mechanism. Let me repeat, you do not solve construct a 6-link mechanism for the sake of 6-link mechanism. You construct it because you need it. That's very important. Now, in this case, there's no solution for using a 4-bar. Now we search for a 6-link mechanism. The way we do it is like this. If I have 6-link mechanism, you see, in case of a 4-bar, if 2 positions were given, I had 6 parameters. Now with a 6-link mechanism, the number of parameters is much, much more. So if I am free, if I have so many parameters, I am free to select 2 links, A0, AB. Attach 2 links. It's what we call diode. A0, AB. The first position, A0, A1, B1, A0, A2, B2. Make sure that A0, AB is not on a straight line in the first or second positions. Make sure that it is movable in those positions. This is a 3 degree of freedom system, open chain. If I attach 3 motors to this system, right? For each revolute joint, if I have motors, I can move this rigid body from this position to this position, 3 degrees of freedom. That's how robots work, right? 3 degrees of freedom. Now, what I have to do is constrain this motion. I have to constrain this motion to 1 degree of freedom. Since I have so many parameters, I have selected A0, AB. Now, I have to design the links to constrain this motion. The first thing I do is, look, consider the motion of the lamp relative to this crank, A0A. To do that, we have seen in relative motion concept, subtract the motion of the crank from that of B0 of the lamp. Meaning, rotate B2, C2, this lamp in the second position, about A0 by the angle A2, A0, A1. This is A2, A0, A1. Keep A0, A2, B2 fixed to each other and the lamp fixed. Rotate all these so that A0, A2 coincides with A0, A1. What you have done is you are looking at the motion of the lamp while you are sitting on A0A, on the crank. Correct? Your fixed link is A0A. Your moving link is the lamp. From the first position to that second position you have found. Correct? Now what you can do is attach draw the perpendicular bisector to any point that you have selected. You see, you have A0, AB. Initially, you have selected, arbitrarily selected. Now you select C arbitrarily anywhere on the lamp. Determine C1 and C2. C2 prime will be over here. Draw the perpendicular bisector, C12 prime. Select a point D on the perpendicular bisector on link A0A. You have a 4-link loop. Now, whenever you construct this 4-link loop, A0, AD is one link. Then you have the 4-link loop C, D, A, B. Now the degree of freedom of this mechanism is going to be equal to 2. Now you can attach 2 electric motors, one at A0, another on D1 or A1, and you will be able to move your rigid body from this first position to the second position. Can everyone see that? Next, I have to constrain one more degree of freedom. I have to, either I will select D1, C1, or A1, AB, or DC in the second position. Now, I select a point E on A1, AB. It need not necessarily be on AB line. I can take it anywhere, outside, but it has to be on AB link itself. It is preferable to select E1 on AB line because in that case I will have the link AB is not going to be too big. The size is because, for example, if I select D1 over here or D1 over here, I can do that. But in that case, as you move away from A0A, this link is going to get larger and larger. If you move away from AB, if you move E away from AB line, the link is going to get larger. Okay? Select E1, determine E2, draw the perpendicular bisector such that it passes through this E0. Now you have attach a link between these two. Now you have a 6-link mechanism that will move your rigid body from the first position to the second. The motion in between, you have to check. Correct? The motion in between, you have to check. You can use relative motion concept to design cyclic mechanisms to move a rigid body from one position to the other. Now, let me repeat, you have more parameters, so the possibility of solving a problem is more possible, let us say. You increase the possibility of solving a problem if you have too many constraints. But the first thing you have to do is, in real life, look, if you can solve a problem by simple rotation, please do it. Don't use a mechanism. Mechanism will affect the cost. Mechanism will make things more complicated. If you can solve it, please do it. If you cannot solve it using a 4-bar, then if you, using a rotation, simple rotation, wheel, then try using a 4-bar or a slider crank or double slider, etc., whichever one is possible. Try not to use slider because sliders have certain problems. You know, sliding prismatic joints have problems. More friction, more locking, but it doesn't mean you don't have to use it. You may use it, but preferably, in most cases, in most design cases, we prefer revolute joints. Number one, it's simpler. Number two, friction is less. Number three, it is easy to manufacture, especially for simple things. It is very, very easy because you drill a hole, you attach a pin in most cases. If not, in other cases, you have to attach a roller bearing. Roller bearings are standard things so that it is easy, it's cheap to obtain. Whereas a slider needs special manufacturing thing. It is much more critical. Okay, so we use 4-bar much more than a slider crank in practice. If you cannot solve using a 4-bar or a slider crank, now you go to have a constraint mechanism. You try a cyclic mechanism. In some cases, you may use 2 degree of freedom systems, especially in recent years in parallel robots. We have 2-3 degree of freedom systems. Still, depending on your problem, we prefer to use a single degree of freedom in most cases. In lots of applications, we prefer using a single because it requires single actuator. Okay, because of the cost, because of speed, mainly for machinery. I'm giving you simple examples where speed is not important, but in most machinery, speed is a very critical thing. Yeah, you want to increase the speed for production, for productivity. So in those cases, use of revolute joints is recommended. Okay, I think I will stop right now. I will stop sharing. I will, if you have any questions, I will be glad to answer. Any questions? Okay. I will